Before we jump onto the problem, first let us know what an oil spill is. An oil spill is any spill of crude oil or distilled products. Occurrence of oil spill causes large-scale economic losses and environmental damage. After the oil enters in water, it extends and forms a big area of oil slick under the role of gravity, viscous force, surface tension. Further, the tides, waves and wind also support the drift and spread of oil slick. Hence, modeling of oil spill is very necessary for its cleanup and to reduce the damage to ecology. After the occurrence of oil spill, there are many phenomena due to which oil is carried away to some other place and also it starts decaying. These phenomena are collectively known as oil weathering processes. Let us see some of these phenomena. First is spreading or advection. Due to the waves and tides, the oil drifts away from the point of spill, which makes it tough to recover. Evaporation. Oil gets evaporated after a certain time of oil spill, which reduces the amount of oil that can be recovered. Third one is emulsification. Some part of oil forms emulsion with water, making some percentage of oil spilled irrecoverable. Next is dispersion. Due to the turbulence in water, oil breaks into small droplets and is dispersed and remains suspended in water. The last is sedimentation. After the oil is broken into small droplets, some of the oil, due to the gravity forces, also settles down to the seabed, makes it not irrecoverable, that part. Now let us understand the problem statement. When an oil spill occurs, the major task is to ascertain the amount that has been released and the pattern of spread of oil with time. After the occurrence of oil spill, due to the surface forces and force of gravity, it starts spreading in all directions. In still waters, after a period of time, the slick attains a fixed radius and is easy to recover compared to rough waters. After getting the radius of slick and knowing the amount of oil spilled from vessel, we can calculate the thickness of oil spill too. Hence, it is very necessary to determine the variation of radius of oil spread area with time and the thickness of oil spilled in open water that we have done in this model. The work done so far. In our approach, we have currently taken in the consideration of oil spill in still water and tried to build a fundamental model of variation of radius of oil slick with time according to the force balance. Next, we have visualized the scenario by conducting a test in pool of water and determined the parameters that affect the oil spill. So before we jump onto the experiment, let us visualize the forces acting. This is the oil interface and water interface, water-air interface. The force of gravity acts downward, the buoyancy acts upward, and the surface tension forces act along the sides. Now let us see the experiment of oil spill in pool of water. Sesame oil has been poured into a pool of water to observe the phenomena. Here we see that as the oil spill is occurring, it forms small globules in water. But it slowly join together to form a single oil spill globule. How the pattern of oil spill had been formed after a long period of time. We can see in the video there were small globules, but here there is a fixed large circular projection has been formed, and of this projection we try to find out the radius and formulate the model.
Let us formulate the fundamental model for surface spreading of oil on water. The assumption that we have taken to formulate this model are as follows. There are no external disturbances like wind, etc. Viscosity, surface tension, density are constant. Volumetric flow rate of oil is constant. There is only one globule of oil present. Now, we will proceed towards the model analysis and calculation part. Assuming that when the oil falls on the water, a circular projection is formed whose radius increases with time. At time t is equal to 0, the oil starts falling at a constant volumetric flow rate V0. Now, let us look at this diagram. In this diagram, V1 denotes the volume of oil above the water surface, whereas V2 denotes the volume of oil below the water surface. R represents the radius of oil slick at time t. H denotes the height of the oil slick above the water surface at time t. Applying force balances on the oil globule, we get equation number 1. Then we apply mass conservation. We get equation number 2. Solving these two equations simultaneously, we get relation of V1 with time. Now let us find height h as a function of V1 and radius of oil slick. Assume that a sphere have a radius r. Then volume of spherical segment will be 1 by 6 pi h into 3a square plus h square. Using Pythagoras theorem, we get a relation of a as a function of h and radius of sphere r. Substituting this value into the equation, we get volume V1. Then we find out the contact angle alpha. Now, after substituting these values into the equation, we get the final equation, equation number 5, h as a function of V1 with respect V1 and r. In a similar way, substitute the value of capital R into the equation and get alpha as a function of V1 and radius small r. Actual contact angle will be pi by 2 minus alpha as shown in the figure. Assume that oil is entering between time t and t plus dt only accumulates on the volume of surface above the water, due to which curvature of the oil above the water changes. In the following diagram, gamma 1, gamma 2, gamma 3 are the respective surface tension between the interfaces. Gamma 1 is the surface tension between water and air. Gamma 2 is the surface tension between oil and air. And gamma 3 is the surface tension between oil and water. As there is no change in forces by gamma 1 and gamma 3, so in the force balance, we can neglect them, but the direction of gamma 2 changes due to addition of oil. This change in force causes an imbalance of net horizontal force on the oil, causing it to increase the radius of the oil by dr. Now we will find the variation of alpha with respect to volume of oil above the water surface. As you can see, we get the equation of alpha with respect to V1, which can be also called variation of angle of curvature alpha with respect to volume of oil slick at time t. Now write the final force balance, which can be also called Newton's second law. In this equation, we have assumed that all forces act on the volume of oil added in time t and t plus dt, whose mass is rho oil V0 dt. We have taken acceleration as d square r upon dt square. because it is radially spreading. Now, as you can see, after substituting all these relations and solving the final force balance, we get the following equation: gamma 2 upon 2r square v1 into pi square r6 minus 4v1 square is equal to rho oil d square r upon dt square. Here v1 is equal to v naught t into 1 minus rho oil upon rho w. The equation of v1 was found out before. So this is a final differential equation that we can solve. By solving this equation, we can get the relation of radius of oil slick at any time t. This equation can be solved by any numerical method.